All right, so continuing with our Chapter 2, Kinematic Graphing, I'm going to introduce to you now the idea of what we call stacked graphs. Now remember, all of our different values here, our position, our velocity, or I should say our displacement, our velocity, our acceleration, are all taking place over time. And all of these things can change in the same time period. So having stacked graphs, what that does is that tells us what is happening with position, what's happening with velocity, and what's happening with acceleration all at the same time. What I mean by stacked graphs is this. Let's see, I'm just going to do that. Oops, I don't want to do that. I'm off on a bad start already. Let's erase that there. Okay, so we're going to do that, and that, and that. So this is position versus time. Instead of the delta, I'm just going to write the x. All right, but you know that means change in position over time. Change position versus time. Velocity versus time. Acceleration versus time. Right here. All right, we're going to do the same thing in these other boxes as well. But we're going to start here. Okay, so if we have an object at rest, and I'm going to draw these graphs in. I'll draw them in red. All right, an object is at rest. Do we know where it is? No. We don't know where on this position thing it is, so that could be anywhere. An object at rest, if you're sitting in the front row and some kid in the back is sitting in the back row, you have the same velocity. That is, you're both at rest, but you're in different positions. So the initial position doesn't really matter. So let's just pick one. I don't know, starting right here. Okay? So I don't even know what that is. 3 meters from the origin. Okay? That doesn't really matter. What matters is the fact that it is at rest. It is not moving. So if it starts out initially at 3 meters from the origin, and it's not moving, it's at rest, then over time, it's going to maintain that same position right there. Let me redraw that because that wasn't very straight. All right? It's going to maintain that position. We're going to have a straight line because at rest means there's no change in position over time. There's no velocity. So you can have a flat line. Remember, velocity is the slope of that line right there? What's the slope of that line? 0, right? So that's at rest. All right, so if velocity is 0 in the same x number of seconds, then what would the graph below it look like? What would the velocity versus time look like? Well, it's 0. It's 0 here and it's 0 here. So the slope of the line here indicates the y value here because now down here velocity is on the y-axis. So we've got no velocity over that period of time. Right? It's not changing. And if there's no velocity over time, remember how acceleration equals a change in velocity over a change in time. All right? Well, there's no velocity, there's no change in velocity, so acceleration is going to be 0 as well for those 5 seconds right there. All right? So the only difference here really is that we have this x. And honestly, this x could start out at the origin as well. So all 3 of these could be a graph on that bottom line. And that would be absolutely perfectly right. But the point is, if an object is at rest, they all have flat graphs because there's no change in the object's position. All right, let's do the same thing for this right here. I shouldn't have drawn those so close to the edge. In fact, I'm going to do myself a favor. I'm going to do that. All right, and so we'll do that, and we'll do that right there. Again, here we have acceleration over time. We've got velocity over time, and we have displacement over time. Okay, if we have a constant velocity, remember, velocity equals change in displacement over change in time, or the rise over the run, or the slope. So that means for a position or a displacement versus time graph, you're going to have a constant slope. So we'll just say it's a constant positive velocity. Doesn't indicate anything otherwise. So we're going to, in fact, let me do this in different color so it kind of jumps out a little bit more. I'm going to do this in blue. All right. Here, we're going to have a constant velocity. That's indicated by the fact that we've got a constant slope. So it's a constant change in position over change in time. Change in position over change in time. Okay? So if the slope right here is the same here and here and here, And what is that slope? Well, it's a positive slope, it looks like to me, right? A positive change in position over time. Then that means it's going to be the same value down here, but it's just going to be the same constant value. So whatever positive slope that is, I don't know, 1 over 3 or 1 to 3, doesn't really matter. It's some positive value. So our velocity is going to be somewhere in the positive. We don't know exactly where, but it'll look roughly like that. Okay? Then what about acceleration? Well, remember, acceleration is a change in velocity over a change in time. All right? Over this time period, is the velocity changing? No, it's not. It has a velocity, and that's good, which means the position is changing, but the velocity itself is not changing. So that means it's got zero slope right here, which means there's no acceleration. So the acceleration, poor acceleration, still has a flat zero slope right there. Flat zero graph. That's all right. That'll change a little bit later. All right? But what if we have a constant acceleration? All right? In fact, this last one right here, why don't we start from the bottom anyway? All right? We have acceleration over time. And here we have velocity over time. And here we have position over time right here. All right, this is going to be interesting because we've got a constant. We'll call it a constant. I'll do this in dark green. All right, we'll call it a constant positive. Oh, that's almost impossible to see, isn't it? That's a positive sign next to the acceleration right there. We'll call it a constant positive acceleration just because we have positive graphs right here. All right, so this constant positive acceleration is, I don't know, let's just give it a positive value. It's constant, the acceleration is not changing, but it is, at least in the positive direction right here. It's somewhere above zero. So it's got a certain change in velocity over change in time. All right? Remember, down here, this y value, this acceleration, is equal to the slope up here, right? It hasn't been too evident over here because we haven't had too many slopes and y values. But here we have an acceleration, which means this is going to create this graph that has a slope, a positive slope that will look like this. All right? If this right here, if the slope here, if the y value here indicates the slope here, then this slope is the same thing from there to there to there to there. It's a constant positive slope. Well, let me undo all those right there. Can I? Darn it, I'm just going to have to do this. All right, so this change in velocity over change in time equals the acceleration, which, by the way, we're told is constant right here. All right, so the velocity is changing over time. How do we know that? Well, here the velocity is 0. And now it's got some velocity, it's got a greater velocity, and a greater velocity, and a greater velocity, and a greater velocity, which means that's going to make this one look very different. Remember how the y value right here, this velocity and that velocity and that one and that one and that one and that one, if we go up one, the y value on this graph, here and here and here and here and here and here and here, equals the slope of the graph before that. That's interesting because we've got a small y value and then a greater y value and a greater y and greater and greater and greater and greater and greater y value. That means we're going to have a small slope, or actually we'll start with 0. 0 slope, and then a greater slope, and then a greater slope, and a greater slope, and a greater and greater and greater slope, which will look like this. So 0 slope, and then after time, some slope, and then after time, more slope, and then after time, more slope, and etc. like that. So this right here is going to be a curved line. You can see how the slope of that line keeps changing. All these little tangent arrows right here are indicating that those are all different slopes. Well, it's because the velocity is changing. The velocity is changing because there is an acceleration. So each one of these affects the one before it. That's why we stack these graphs vertically, because we can see exactly what's happening to all these graphs at various points in time. All right, so this is kind of your little kind of practice for this. The next couple videos are just going to be us going through stacked graphs and just doing some example problems. So I'll see you on those.